Hi folks, welcome to physics. In the last physics lesson, we looked at equilibrium, when the net torque on something is equal to 0, so that either it doesn't rotate or that it rotates at a constant rate. Think ladders leaning against walls, teeter-totters, fidget spinners, tops, things that are spinning at a constant rate. This lesson, we're going to go a little bit farther. We're going to look at what happens when things are not in rotational equilibrium. That means that the net torque on these objects will not be equal to 0, and they will not be rotating at a constant rate. In order to do that, we're going to need to introduce a new term called rotational inertia, and we'll define that and describe that here in just a few minutes. But I would like to start with looking at the translational case. We talked about that a lot last semester. You're familiar with that. So we're going to start looking at a case when the net force does not equal to 0, and then compare that to what happens when the net torque is not equal to 0. Consider the 4 objects in translational motion. Take a moment and rank them from lowest to highest acceleration. If you need to pause the video, go ahead and do so. As we look at ranking them from lowest to highest acceleration, the first thing we need to do is look at the net force on each object. You probably noticed that the net force on all of them is the same, 3 newtons to the right. That means that the acceleration for each of these objects will be based on its mass. The smallest amount of mass will have the largest acceleration, and the largest amount of mass will have the least amount of acceleration. For our ranking, that means that B will have the smallest amount of acceleration, with its 6 kilogram mass being the largest, and D, only having a 1 kilogram mass, will accelerate the most. Some objects resist a change in motion more than others. The word we give to that is an object's inertia. Roughly defined, inertia is an object's resistance to a change in motion. Let's call that acceleration. Which will have more inertia, a bowling ball or a balloon? Clearly the bowling ball, but why? Because it has more mass. For linear motion, mass is what measures an object's inertia. Newton's second law tells us that the net force on an object is equal to its mass multiplied by its acceleration. That means that the more mass something has, the less it will accelerate. As m increases, a decreases. We have a similar case for rotational motion, but here the inertia doesn't just depend on mass, so we call it the rotational inertia, or the moment of inertia of an object. And instead of m, we use the variable capital I. Newton's law for rotational motion looks like this. Instead of talking about the net force, we now talk about the net torque. Remember, torque is just a force that can cause rotation. And instead of talking about linear acceleration, we talk about angular acceleration. In this case, we have a similar situation. As the inertia increases, the angular acceleration decreases. Looking at this example of objects rolling down a hill, how could you determine which one will have the most inertia? Take a second, rank them from lowest to highest rotational inertia. Here they are at the finish line. What do we use to determine what will have the least and most amount of inertia? We can look at their acceleration. The objects that accelerated the most will have the smallest inertia. So the object that came in first place, our yellow ball, has the least amount of inertia. And the object that came in last place, our green hoop, has the most rotational inertia. So rotational inertia measures how hard it is to start or stop an object from rotating. But what besides an object's mass can make it difficult to rotate? Rotating a hammer by holding it at the middle is much easier than rotating it by holding it at the end. Why? Same mass, but the distance from the axis of rotation is different. The factors that influence an object's rotational inertia are its mass, and how far that mass is from the axis of rotation. For a simple point mass that's rotating a distance r from an axis, the rotational inertia is equal to the mass multiplied by the radius squared. This applies to any small object that is moving in a circular path. Since the rotational inertia is the mass multiplied by the radius squared, it will have units of kilograms times meters squared. How would the rotational inertia of an object change if the mass's object doubled? Since the inertia is proportional to the mass, if the mass doubles, the inertia will also double. How would the rotational inertia of an object change if the radius doubles? If it was twice as far from the axis of rotation? Since the inertia is proportional to the radius squared, if the radius doubles, the rotational inertia will quadruple. What if the mass isn't concentrated at one point? What if it's a more complicated distribution of mass? What you see here are several differently shaped objects rotating around some sort of axis. The equation for the rotational inertia of each one is shown underneath. If you examine those equations, you notice a few things that they all have in common. All of the rotational inertias are equal to something, usually a fraction, multiplied by the mass times the radius squared. The exact value of the fraction is not something you will need to know, but you should have a good sense that the rotational inertia is always proportional to the mass times the radius squared. In fact, if you broke any object down into tiny pieces and added up all of their individual rotational inertias, that would tell you the rotational inertia of the entire object. To summarize, whenever we have an object that experiences a net torque, it will not be in equilibrium. Newton's second law for rotational motion tells us that the net torque on an object will cause it to accelerate or to have a rotational acceleration, and that acceleration will be inversely proportional to the rotational inertia of the object. The higher the rotational inertia, the more torque it takes to accelerate an object. The rotational inertia of an object is determined by the object's mass and the distance of that mass from the axis of rotation. These are the two new relationships that this video talked about. As you solve puzzles, you will find it useful to remember a few other relationships as well. In particular, the definition of torque. To calculate the torque that a force provides, the torque is always equal to the perpendicular component of the force multiplied by the lever arm, or the distance away from the axis of rotation that the force is applied. The other relationship that will be helpful for you is to remember what we mean by rotational acceleration. Rotational acceleration is equal to the change in rotational velocity divided by time. Hopefully that was helpful. Keep these 4 equations in mind as you work through the practice puzzles to follow.